Hi there everyone. In this video we're going to look at hypothesis testing and the three different types. So as you can see on the screen now, there's the PMCC, there's the binomial, and there's the normal distribution. And how do we know we're involved in a hypothesis test in the first place? Well, first of all, you're looking for a significance level, and this will be shown to you as most likely 5%. Sometimes 10, sometimes 2.5, sometimes 1. You're also looking for different words like the mean has changed, or the correlation is less than expected, or the number of bowls with a crack in are more than expected. So you're looking for those sorts of words combined with a percentage of some kind. Now with the PMCC and all of the others, there are hypotheses, and the first one is H0 and the second one is H1, and they all change depending on the type that you're doing. So with PMCC, it's a row, that's like a fancy P. And when we start off, we're saying the correlation between two variables, so this would be with a scatter graph, something like this, okay? So this would be for a -1, for example. You'd expect a linear line there, for example. So we'd start off by saying that there is no correlation, and that would be the same for every PMCC test that you do. There'd be zero correlation. And then you'll either be looking at, has it changed, not zero, is it less than zero for negative correlation, or is it more than zero? And that would depend on the language that I've highlighted up there in blue. We're going to do a question on each of these in a minute. This is just an overview page. When you move over to the binomial, this is discrete data. So this is things like the number of bowls with a crack on it, the number of people, the number of flowers, number of flowers that turn blue in a bag, for example. If you can say the number of, it is discrete data. And when we're looking at the binomial distribution, the first hypothesis is P equals, and then H1 would be P is not equal or less than or more than the same. And you'll have some parameters, so let's say x is distributed binomially, and you have your parameters of n, so let's say it's 50, and the probability would be 0.1. So the first one, you'll assume the probability hasn't changed, so then it could be less than 0.1, more than 0.1, or just not equal to 0.1, or has changed from 0.1. The normal distribution, that is continuous data, so this is like weights, times, something that is continuous. Very easy to separate all three when you look at them all at once. Let's say it's distributed normally, and we have a mean of 120 and a standard deviation of 8, for example. So you'd expect to see something very similar to that. Now the normal, it's a little bit different. The normal, when you're taking this is the mean, right? So when you're taking a sample, this is the population mean, this 120, and this is the population variance. So when you have a sample mean, and you notice I've put the mean symbol like x bar, we'd say the sample mean is distributed normally, and we'd expect the average to stay the same. Let's talk about the mass of a tennis racket being 120 grams. It's a little bit light for real life, but let's just go with it. And if we took, say, 50 tennis rackets, we'd expect the mass to still be the same because they're produced in a factory by machines. However, we might expect the variance to be ever so slightly smaller because less varied, because we're only looking at 50, let's say, than 50,000 that are probably produced each year. So for the variance, what we do is we divide it by the sample size, just to account for that less variation. So we're finding the mean of the variance. So that is the first step in doing the normal. And for this one, you would have your two hypotheses, and you'll notice we're talking about the mean here. So is the mean 120, or has it changed from 120? Is it less than, or is it more than? That's an overview. So let's have a look at some questions. I'm going to do these live with you. So if you're watching this back, why not just try and take this question in and pause it, have a go yourself. or you might do that the second time of watching, like maybe tomorrow or something. Okay, so looking at this question, I can see that it's a scatter graph of some sort, and it looks like it curves like this. Now, when we normally look at correlation, we're normally looking at a straight line, but this is clearly correlated. There's clearly a pattern here, but it's definitely not a straight line. So on this first question, it says, interpret the nature. And you'll probably find that 9 times out of 10, you can write a negative linear correlation. Now, linear is used to represent a straight line. I would avoid saying linear. You could say negative correlation, but you're far safer to saying something like, this is heart rate and this is minutes. So the more time spent exercising, sorry, it's going to take a little while, more time spent exercising, the lower the resting heart rate. I think for all the next ones, I'll just verbally say the answer rather than write it down. Lower the resting heart rate. That's describing a negative correlation. If you wanted to, you could also say, therefore, a negative correlation. I would definitely avoid using the word linear because it's definitely not a straight line. Okay, so they're telling us something about the code in data, and I would expect to see this because it's exponential. And if we quickly scroll down here, you can see here's the exponential curve. So this curve is used to model this data, and for this type of question, to create the equation, you have to take logs. So seeing this isn't scaring me. I'm expecting to see that when I see an exponential curve. The bit that's odd is it's kind of not needed until later on. And you can see here PMCC, so on that first one. And the PMCC is this value, and we often call this value our regression value as well. So R is minus 0.897. What that represents, R is not that funny row symbol, is this is our sample correlation. So we're going to test our sample correlation against the population, and then we're going to make our decision. So state the hypothesis clearly. So here we go. So H0 row is 0. We're always going to start with that on a PMCC, the correlation is 0. H1 row is something 0. So let's have a quick look. Negative correlation. So that's what we're testing. I like to draw a picture here. So here's a quick number line of probability, correlation, sorry. So it can be -1, so a perfect linear negative correlation, no correlation, or a perfect positive correlation. At this point, we're going to have to look up in our tables now. Oh, I don't have those with me, which is slightly awkward. So you can have to do that. In fact, I have done this question this morning with someone else. Let me just find it. Here it is. So it's minus 0.3887. Okay. So how would you find that? So minus 0.3887. What's another 8 in there? So squeeze it in. This is our critical value. That's from your stats book. It's on page 191 in your stats 2 book, or when you're during an exam, you have them given to you in your exam booklet. So minus 0.3887. That is your critical value. So it's really important to write this line, which is reject H0 if our regression value is less than or equal to minus 0.3887. Critical value, critical region. So make sure you write it. All right, and what was our value? So our value was over here, our sample correlation value. So therefore, we are rejecting H0. So therefore, there is evidence to suggest, this is where I'm just going to verbalize the answer here. So evidence to suggest a negative correlation between the heart rate and the time spent exercising. There you go. But it's important to have this reject H0 and this as part of your conclusion. That's PMCC. That's pretty straightforward. If it was a two-tail test, you'd look in both of these tails and you'd have 2 critical regions. But for this one, it's not. I might as well finish this question off as well. So with this one here, we have h equals am to the k. And we saw from earlier, our variables are the heart rate and the time spent exercising, so h and m. So we're going to take logs. So if we take logs to both sides, and I'm gonna just do it in its correct form here. If you're unsure where this came about, then you take logs to both sides, you split them up using the addition law, and the power law comes down. That's why that k is down in front. So when you look at this, you have a variable h, you have a variable m, and the others are your constant terms, and this is taking the form of y equals mx plus c. So our constant variable term, mx, so the k is our gradient, and you've got the gradient here, is minus 0.05, and our constant term all on its own in linear graphs is our y-intercept, and our y-intercept is here, 1.92. So a is 10 to the 1.92. So to finish this off, h equals 10 to the 1.92 times m to the minus 0.05. And there you have it. Right, let's have a look at this question. So now we're talking about a dentist. From past records, 10%. So I've got a probability is 10%, 0.1. Arrive late. Even after that first line, I know it's a binomial distribution because it's the number of people that are late. And here we go, the magic words, change in proportion, change in the probability, same language. We've got a sample of 50. So straight away, if you were to write this down, you're going to get yourself a mark somewhere along the question. Probably one of these three here. No hypothesis. Okay. But actually, I've done something a little bit naughty here. I've introduced x, but I haven't defined what it is. So x is the random variable. Oh, what am I doing there? Be the random variable number of people late. That'll do. So now we're ready to go. So our hypotheses, h0 is probability. We're talking about the probability is 0.1, or has it now changed? It's no longer 0.1. Okay. Let's have a quick look at what we're facing. So we could have no people late, or we could have 50 people late. And I always like to draw this picture. We would expect 10% late, so we'd expect 5. This question is asking us about the critical region. So this is the harder variation. You just haven't got a number you could just pop in. In fact, I do all of my questions using the critical region and then just do what they're asking you to do in part D. So there's a cutoff point here, like an observed value here, and an observed value here, where it becomes significant. And we're looking for how far up we can push the first one and how late we can push the second one to be deemed significant. Why would that not go away? Okay, so we are going to reject h0 if, again, it's that sentence you must write. We're going to reject h0 and we'll just see how far we can push this first one, and it has to be less than 2.5%. Okay, so there's that other language that we know in a hypothesis test is here, the 5%, the 2.5%. Remember, it's two-tailed, so that's why it's halved. Okay. Now that's fine. Our calculators are set up. We can do that one pretty easily. The upper tail one, so the second x, that's a little bit more confusing. It has to be higher than this value and be less than 0.025. And our calculators aren't set up. If this was a 6, we'd want 6, 7, 8, 9, 10, all the way up to 50. We wouldn't want 0 to 5. So for that reason, this is the same thing. And for the same reason, if we just jig it all around, we don't want a negative here, so we want this positive. We're looking at this scenario here. Now, I'm going to use my calculator to do this. You can just use your tables, but I don't have them in front of me. So I'm going to go onto the binomial distribution. You can do it too while you're watching. I'm going to go into the binomial CD option and hit list. And, you know, I'm going to put the numbers 0 to 5 in for the first one. The second one, I'm just going to be safe. I'm going to go up to 15. So I'm just going to, bear with me while I put these in. I'm going to hit OK. I'm going to put the parameters in, 50 and 0.1, and it's just having a little think. Okay, so let's look down for the first one that is less than 0.025, and it is 0. So when x is 0, I get 0.0051. Please get in the habit of writing your p-value. So that's the critical value. What that actually means is the only time you would have a significant improvement is when the number of people late are 0. And there is a 0.51% chance of that actually happening. If you go down to the other end, we have to go bigger than 0.975. We get an observed value of 9, which means that you'd have to have a value of 10. The probability of it being a 9 is 0.9754. Right, get in the habit of writing that down. Okay, so what that means is this is 10. That's an observed value. So the critical region, the number of people that are late, that's why it's a capital now. The capital is very important, is more than or equal to 10. To find more than or equal to 10, that is 1 minus up to and including 9. That's why you should get in the habit of writing these numbers. So take it away from 1, and you get a 2.46% chance. Please get in a habit of doing it. Also do this for your examiner. Here's my critical region. Look, it's really easy to find. Give me all the marks. Actual significance. So they either say this or they say the p-value. If they say the actual significance, you add them up. So what's that? 2.97%. If it was the p-value, it's the decimal of that, so 0.0297. Okay, so nice and simple. We have 15. 15 is greater than 10, so therefore reject H0. And you'd have to say there's evidence to suggest a change. Was it change? Yes, a change in proportion. Of people being late, so I'll let you fill the rest of it. Okay, on to the final one. So they've defined it. We're told it's D for diameter, that makes sense, and it's a normal distribution. So I'm just going to start writing that. D is distributed normally. We have a mean, 0.58, no idea why they've chucked the extra 0 on there. And we have a standard deviation. All right, cool. So there's no need to use the standard normal to find anything. So the mean is serviced, machine is serviced. Random sample of 50, that's important. And to see if the mean diameter has changed, here you go, here's the magic language, from the 0.58. Okay, so I'm going to write over here my hypotheses. So the mean is 0.58, or has it now changed? Is not equal to 0.58. So we've got a two-tailed test. So what you've got to remember is to do this. It's a sample mean, so the mean sample. We'd expect the mean to be the same of all of these bolts, whether it's 50 or 10,000 or 100,000, we'd expect the mean to be the same, but we'd expect a smaller variance. So the variance we're going to divide by our sample size. So let's type that in. So 0.015 squared and divide it by 50. I'm just going to change that to a decimal quick. So that is the same as 0.58. Well, the variance is 4.5 times 10 to the minus 6. That is your variance. I would personally now square root that, just so it's in the form that we want. So it's 0.00212, and that goes on. And that's fine. I'm going to use that exact number. I'm just going to, I'll store it if I need to. Let's see if I do. Right, so here we go again. Significance level language. We've got critical region. That's another language. We've got hypotheses. That's another bit of the language. And let's have a look. So the mean is calculated to be that. So is that enough to change? So draw a picture. Oh, that's a terrible one. There we go. Label it correctly. We're looking at the sample mean. Our sample mean is 0.58. we have a result of 0. I'm just going to change colour so it's easier to read, 0.587, and what's the probability? So I'm going to reject H0 if the probability that our sample mean being bigger than 0.587 is less than or equal to not 1%, because it's a two-tailed test because of this. So it's 0.005. There's my statement, and that's really, really important. So let's go into the normal CD. Our lower is 0.587. Our upper is something ridiculous. So the mean is 0.58. I'm going to use my answer button for my standard deviation. Hit execute, and my answer is 0.0004837. Okay, so comment on it. So reject H0 if it's lower than this, so therefore I reject H0. Now I'm going to say there's evidence to suggest a change in the diameter. And that's it. So there's evidence to suggest a change in the diameter. So we've run through all three. Hope that makes sense. Any questions, do come back to me.